Virtual method is basically when you're talking about subclass, you inherit a method, and then you override that method with the same signature. And so what happens is this method is the one, so when an object of this type comes in, it executes this method. When an object of this type comes in, it executes its own method. That's virtual. But there's another virtual in C++, and I'll get to that a little bit later. It's called virtual inheritance. Now I know what you're saying. Public inheritance, private inheritance, protected inheritance. What's virtual inheritance? Well, it turns out we can add the word virtual to any of these. So we can have public virtual, protected virtual, or private virtual inheritance. Crazy, but it's going to make sense when I explain it. So it's not going to become, it's not going to be more complicated, but it will give us another qualifier, another adjective, if you will, something to explain. Okay, so I wanted to show you some. So today we're going to cover quite a bit of topics. We're going to do these virtual functions. We're going to do virtual inheritance. We're going to do. I think what I may do is skip. Remember the offset pointer to members? I'll cover that very quickly, but then I really want to spend time and cover design patterns. So I'll give you lots of areas of design patterns. We'll talk about what those are. So lots of things to cover, but I think we can get everything done. So I want to just show you some examples of code. So the first thing is, first thing you're going to notice is that we have a class called num, and then integer is a public subclass, and real is a public subclass. So a number, num is basically, notice it has a constructor that's inline, does nothing. It has a next pointer, which is a pointer to itself, same type. And then it has a method called display, but the method display, it says virtual, which you've seen before. Void is the return type, name, parameters, but then we have a special thing that says equals 0. Okay, so we call this pure virtual method or pure virtual function. What it means is, yes, display is a virtual method, just like any other virtual method with the same signature, but because it's pure equals 0, that means I'm never going to code it. So a pure virtual method is virtual, but it's pure. Pure means, not untouched. So no code will ever be written for this method. So why would we want to have a pure virtual method? The reason is because num is like a number, general number, but integer or real are more specific types of numbers. We would like both of these subclasses to have a method called display with this signature, but we don't want to code it because it doesn't make sense here. It makes sense to actually code them when we actually know what the properties are going to be. The property of an integer will be an int value. The property of a real will be a real float value. But the num class has no property, so it doesn't make any sense to code it. So we want to have a collection of nums so that they can be a mixture of this and this. Because this method is pure virtual, we cannot create or construct any objects of this type. Because this is a pure method, pure virtual method, therefore the class cannot be instantiated. We say that this class is abstract. It's an abstract class. No way can I say new num. Why not? Because this method is not coded, so this class is not ready to be instantiated. So when we create a subclass of integer of a subclass of num, notice that we inherit this method, and then what are we doing? Same signature, right? Void, display, no parameters. Here comes the code. So we are coding this method. Cout integer equals, and we print the value. Easy, right? When we do the same thing for the real class, our property is a float called val. And we override the virtual method again, cout float equals val. Okay? So pretty straightforward, I think. Any questions about that? So let's take a look at an example code. So this is a main method, right? We're going to use those three classes. We'll come back to this for a second, but I'm going to say main method is here. Notice that I have an array of 5 pointers to num. Pointers to num. Remember, I cannot have num objects. But remember, an integer is a num, and a real is a num. So if I have a pointer to a num, it can point to integer objects or real objects. Okay? So this is an array of 5 pointers to num. Now here I am constructing 1, 2, 3 integer objects and 2 more real objects. Okay? Now I am going to go into this array at index 1 and I'm going to put in the address of the first integer, here the address of the second, of the third, of the first real, of the second real. So my array is pointing at integer, 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 real, real. Remember, ampersand I, what type is that? What type is ampersand I? Ampersand I. What is ampersand I? Okay, so therefore what type is it? No, int. That's a class. So what type is ampersand I? Nobody's got it right yet. It's an integer pointer. It's an integer pointer. But an integer pointer is a num pointer. So therefore this integer pointer can be assigned into a num pointer array. Get it?
Yes.
Okay, so now what I'm going to do is I'm going to look for I or C equal to 0 less than 5 by 1, A sub C. So A sub 0, A sub 1, 2, 3, 4, that's a pointer, right? Because it's an array of pointers, so A sub C is a pointer to sometimes an integer, sometimes real. So this pointer, I'm going to use the arrow, which is the pointer dereference operator, and I'm going to call display. Now what's going to happen is, on the first value, when C is equal to 0, A0 display will call the display from integers, because A0 is an integer, or A0 star, the dereference A0 is pointing to an integer object. So when C is equal to 0, it will be the integer display. When C is equal to 1, it will be the integer display. When C is equal to 2, it will be the integer display. But when C is equal to 3, this will call the real display. And when it's equal to 4, it'll call the real display. We call this a polymorphic call. Because if you look at it, if you look at this now, and you say, what is A? A is a num pointer array, so A sub C is a num pointer, so therefore this must be the display method from num. Nope, it can't be the display method for num, because num objects cannot exist, because it's an abstract class, because it has a pure virtual method. But we can't tell that we can't tell that nums are abstract. We can't tell that. We can tell it from the previous slide, but it doesn't really make any difference. The idea is that whenever A sub I is pointing at an integer or is pointing at a real, the correct display method will fire. Looking at this code, we cannot tell which, this is not a method. It's a set of methods. Because display is sometimes calling integer display and sometimes calling real display. Those are two different methods. Those are methods in two different addresses in the code segment of the computer. They're in different locations. So therefore, sometimes we don't like to call this a sometimes you don't want to call this a method because it's really two methods. And if we had another subclass, it could be 3 methods. We call this a message. That's kind of the OO, object-oriented terminology. when you're so in a sense, you're taking a pointer and you're sending it a message. Say, I'm messaging you, I'm asking you to display. Whatever that means. Could mean this code, could mean that code. So as this thing is looping, this message triggers different methods for different objects. This is what it means for it to be polymorphic. And polymorphic means, in Latin, it means many forms. Many forms. So this one method is connecting to many implementations of the actual method. Because the num has a pure method. All right, so now what I wanted to show you, what I wanted to show you is the show method. Well, the show method, I simply stuck this method. This is a complete method. This method takes a num by reference and refers to it locally as nr. And it says nr.display. Now the reason I'm showing this to you is because I'm calling it here. A sub 1 is a pointer to an integer. Star is an integer by reference. So the integer goes into a num reference because an integer is a num. And therefore when I say nr display, the method called here is the integer display. When I say show star A4, A4 is a real pointer. Star is a real taken by reference as a num. When I call display, the real display method works. Now the reason I'm pointing this out to you is I want you to understand that in order to have correct polymorphism in C++, you must pass the object by reference or by pointer. If you pass an object by value, polymorphism is not possible. So, for example, if I did this, there would be a problem. First of all, I'd have to take away this, right? And I'd have to take away this, which might be closer to correct, but there would be a problem. The problem is that A1 is an integer, NR is a num, and integer is a num, but because I'm passing it by value, the display method will have to come from num. But there isn't a display method for num because it's pure virtual. You see the problem? Okay, so let me go back and change something. So you understand what pure virtual means, right? So we create these pure virtual methods so that subclasses can be asked to do the behavior here, even though it's not defined because it's pure virtual, but they can then override real implementations, and then we can have collections of nums, which are really collections of integers and reals. We could even have another subclass called fraction, which is a num, and the display would be different, right? 3/4, whatever, right? You get the idea, right? Now, one more thing I wanted to point out to you. If I were to get rid of this virtual, well, I'll keep the virtual, but I'll get rid of this, okay? So no longer is it pure. Well, if it's not pure, I have to either implement it in the H file, in the CPP file, or in line. So I'm going to do it in line, okay? So get rid of this, I'm going to say cout. This is not a good method. I'm going to just say cout hello. Okay, you get it, right? Simple, okay, kind of stupid, but all right, it works. So now it's still a virtual method, which means that these guys are still going to override their own here. But now we have an existing method called display, which is used. Okay. So now when we go, if we change this implementation such as this, and we go to our program, specifically if we go to this area, A1 is a pointer to integer, star A1 is an integer. By reference, it goes into num. And now what displays? Integer display. But if I cover this and everything else is the same, once I don't pass it by reference, the display method will say hello.
Yes.
Okay? So in order to get polymorphism to work, you have to pass the parameter by reference or by pointer. Here is an example of accessing the object through the pointer. Okay. So again, if I wanted to have if I wanted to do this, another example of show. If I wanted to send, for example, let's call it show 2. Show 2, and I wanted to send in A sub 1. What type is A sub 1? Integer pointer. So let's write the method show 2. So we're going to say void show 2, and we're going to take what? Num what? Match the type.
Star.
Num star, and I'm going to call it P, and then I can say basically at that point P pointer display. Okay, so will that give me polymorphism? Will that, so because I can say this way, I can also say show 2 A sub 4. The question is, will that be polymorphic? Is it going to give me the right method for the right object? The answer is yes, because I'm passing the object by pointer. So passing subclasses by pointer or by reference enables polymorphism. Passing them by value, you lose polymorphism. If you are looking at this method right now, can you tell me what method will execute anytime for this method? No, you cannot tell. Why not? Because you don't know what type of parameter is the actual parameter. If it is an integer, it's an integer display. If it's a real, it's real display. If it is a fraction, maybe it's a fraction display. You cannot tell me what this is, right? Right? Neither can the compiler. Neither can the compiler. So the compiler cannot decide at compile time, oh, when I get an object here, I'm going to go to this address, because this method, the display is at this address. It doesn't know which code is going to execute because it's polymorphic. So what happens is the runtime system, when the system is actually running the program, there is something called VMT, which stands for Virtual Method Table. And it has information here. For example, like if you are an integer and the method is called display, then you're going to use this address, 0x address. But if you are a real and the method is called display, then it's going to be a different address. You understand what I'm saying? So when an object comes into here, C++ runtime system has to determine what kind of pointer is it. If it finds that it's an integer pointer, it's going to realize that it has to go to this address. But if it's not, the next time I use a different one, it has to go to this address. So this VMT, virtual method table, is dynamic. It's run by the runtime system, not compiler, cannot decide. And we call this, and I mentioned this before, so I'm going to say it again, this time very quietly so you can hear me. And it's called late binding. Late binding is the use of virtual method tables to make a decision at runtime what code to jump to. We don't know what code to jump to. We don't know what code to jump to. But if I erase this ampersand, I know which code to jump to, and the compiler will decide it. Well, if the compiler can decide it, that means different types in the future are going to call the same method. So if I got rid of this ampersand, everybody would just say, hello, 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 because I can decide it early binding at compiler. All right. Okay. Yeah, so now this example basically takes these three classes. So if you look at it over here, why do we need this num class? Well, first of all, we need the num class because it has this virtual display so that we can treat all num subclasses as the same. But it also has this pointer to a num. What's a num? A num is one of these. Or this is a num, or this is a num. So one of these can point to a num instance, which doesn't exist, or an integer instance, which could exist, and a real instance. So this is just an example of creating something. So here, we already seen that. Okay. So we've seen already this method show. So let's look at a method called IInsert, FInsert, and showAll. Okay. So IInsert means I'm giving you an int, and I'm giving you, what the heck is that? Head. What type is head?
Num.
No. Head is a num pointer taken by reference. That's the most complicated thing you can have. So you're taking a pointer, so head is a num star, or a num pointer, taken by reference. So what does it mean taking a pointer by reference? Well, it's nothing special. It just means that the actual pointer and the formal pointer are referring to the same location. There's no copy. There's no pass by value. Okay, so same thing here, same thing here. So what's going to happen here is I'm taking this pointer. Now, basically, the head represents the head of a list. I'm going to make a list, a linked list. Very simple kind of linked list. So what's going to happen is if you give me a number, n, I will create a new integer object. You understand, right? From those classes. I will create a new integer object with n as a parameter. And I will have t pointing to it. Notice that I'm creating an integer and I'm pointing to it with a num pointer. So this is pointing to this newly allocated dynamic object. Then I'm going to t pointer next, which is the next property of the integer that I just created, and I'm assigning it the value head. So now what's head? Head is actually a pointer to another node. So I'm saying the next field of my node is the head. I am inserting my node before the head of the list. So it's an insertion in the front. And then I'm changing head to point to me. Does that make sense? Or are you totally confused? How many people are confused? Okay. So suppose we have something like this. So suppose we have a list that looks like this. So we have 3 is pointing to another node, and this node is 2.7 is pointing to another node, and this node is 1, and this node is null. So I have, let's say, something like this called list. What type is this? Integer. What type is this? Real. What type is this? Integer. Okay. So what I'm going to do is I'm going to say I insert, and I'm going to put in for the first parameter, let's say the value 8. And then I'm going to put list. What type is list? Well, list is obviously a pointer to num. It's a num pointer, which is, I'm calling it head here, which is the num pointer. And so this is my call. Let's see what's going to happen once I call. Once I call, the first thing that's going to happen, I'm going to create a local t, which is a num pointer, and allocate it to a new real n. No, not real, new integer n. So it's going to create something like this. I'm going to create this, and I'm going to put this into the constructor. So I'm going to put that 8 in here, right? Yes. And then t is pointing to it. That's what happens here. Then I will go to t pointer next. Well, t pointer next is this field. That's the next field, right? And I'm going to set the t pointer next to head. Well, head is what I call, remember, what went to head? List. So therefore, head is the same value as this. By reference, change head, change list. So now, what I'm going to do is I'm going to say t pointer next is equal to head. Well, since head is pointing here, now this guy is pointing here. And then I go with head and I set it to t. By doing that, head is going to here. When this method exits, this local is deallocated, but because list and head are passed by reference, list has also changed to here. And of course, head becomes deallocated because it's a local, right? You see what we just did? So we were able to insert at the head of the list. Do you see why we had to change this? If I didn't have this one, what would happen is everything would look just like this. Head would look like this. Sorry. Yes? No. Head would look like this, but list, because it's coming by copy, would stay over here. If I got rid of that. And that way, when head is deallocated because it's local, I would have a list that looks like this, but my list would still start at the original node. I have to change the list. List is a pointer, so send the pointer by reference. If you want to change something, you send it by reference. If you want to send something, send it by reference. If you want to change a pointer, send the pointer by reference. You want to change an int, send the int by reference. You want to change a rational, send the rational by reference. If you want to change an object, send it by reference. Or send a pointer to it, because if you send a pointer to it, this copy pointer will be going to the same place. But that's a pointer. So two different pointers can point to the same thing. But if you don't send a pointer, you send a thing, send it by reference. Otherwise, you can't change it. When we send arrays into functions, do we send them by pointer or do we send them by reference?
Pointer.
By pointer. If you said pointer, then you know exactly what I'm talking about. Because basically, we don't send the array by reference. We send arrays a pointer, so we just send it. We never have a reference with an array. We just send the array name. And then we take it as an int pointer or something like that. So we just have two pointers to the same array. Well, because we have the same pointer to the same starting element, we can change the starting elements. But we can't change this. For example, suppose I had P and P was pointing at an array. So let's say I had an array allocated like this, right? Now, let's say A is the actual array name and P is just an int pointer. If so, I can call a function, I can send A, and I can change the elements. I can call the same function with P, and I can change all the elements. Right? Now, if I pass it by reference, if I take this by reference, and inside the function, and let's say the function is out here, let's say I had something called Q. If I pass it by reference, let's call it int pointer reference, and I say Q++, what's going to happen, it's actually going to move this P pointer. Because I sent this by reference, I can change it. Of course, this is a const. You won't be able to do it. All right. The other thing I want to talk about is virtual inheritance, and I'll explain to you in a very, very simple way. So, we already know everything about inheritance, public, private, protected, and then the properties can be public, private, protected. We know what a client is, we know what a subclass is, we get all that stuff. So where does virtual come in? Well, suppose, let's use this example here. So suppose I have this class called num, since everybody's famously recognizing it. So num is a class. And I know that I have a subclass. So in the subclass, I created something called an integer. And then I recorded another class called real. Okay? Now, for some reason, let's say what I wanted to do is I wanted to have a class that has everything that an integer has and also everything that a real has. Are you with me? Which means I want a class that has a property of int type as well as float type. Because the integer has a property of type int, and the real has a property of type float. So what I'm going to do is I'm going to create very funny class name, interreal. Integer, real, interreal. And I'm going to subclass here, and I'm going to subclass here. Are you with me? Okay. So this is superclass, these two are subclasses, and this is a subclass of both these. We would write the code something like this. Class interreal colon, and we might say, for example, public integer comma public real. Get it? So we call this multiple inheritance because we're inheriting from two. And some languages let you do that, C++, and some languages don't, C#, Java. Do not let you do that. C++ lets you do that. But that is got some positives, it also has some negatives. Because think about it, what's happening is that the class interreal is inheriting everything from integer and from real, but integer is also inheriting from num, and so is real. So actually, if you think of integer, integer is like an integer and a num. And real is a real and a num, and you're inheriting everything from both of them. So actually what you're doing is you're inheriting num two times. Now what does that mean? Well, what it means is that you're getting that next pointer from one direction, and you're getting another copy of it. You have two next pointers. And you would have two of anything that exists here. It just gets passed on here and passed on to you twice. So you can actually you actually have two next pointers, which is really strange. So you could have like a next from here, you could have a next pointing to one node, and a next from here pointing to another node. You could select, I want the next from integer, I want the next from real, and they're different properties. Well, that's really not desirable. I mean, the idea for the num was to have a display virtual method and to have a link, not to have two links. So we typically do not like inheriting the same thing twice from two different lines of inheritance. If you look at this, okay, if you look at this over here, okay, if you put your finger through here, you have a ring. And on top of the ring is a diamond. This is called diamond inheritance because this is the shape of a diamond. And you see diamond inheritance, it looks like a diamond. And so diamond inheritance, I should make the finger a little bit smaller, it's a very fat finger. It would look more like a ring, so let's see if I can make my artistic look better. All right, so that's my ring. So diamond inheritance is legal in C++. You can even have a fatter diamond, meaning that you can have another class which inherits from num, and you can inherit from that too. So multiple inheritance is okay. Now, we don't usually want to inherit the same thing from two different ways and have double copies of things, because then I may be referring to one pointer in one piece of code and then a different pointer in another code, and I could have inconsistencies. Which next do you mean? You mean the integer next or the real next? Oh boy, I don't know. I'll take a shot. Whoops, bad decision. So what we'll do is we will add as part of the inheritance virtual here and virtual here. This virtual keyword is not like a method virtual, not like a pure virtual or non-pure virtual method. This is virtual inheritance. And let me tell you something. So I could say integer virtual public num, real virtual public num. Okay, so imagine I added this and I added this here. How does it affect integer? The answer is it doesn't do anything for integer, one way or another. How does it affect real? Nothing. What happens is when you have a virtual inheritance from a class, and then it turns out that you're inheriting from two lines that have virtual inheritance, what happens is you only get one copy of the stuff that was virtualized in these inheritances. And so now you would only inherit one next pointer. You would not have two. There could be no error. So you'd have everything appendant here, everything appendant here, and one copy of everything here. Questions? Any questions? Yeah.
Like if it's creating a one copy, single copy. So from where it is coming, from a decay point or from read?
No, it doesn't matter. Now you can think of it as truly coming from num. You can think of it that way, because you can no longer distinguish about it. Which one is it really coming from? I don't know. I don't know if anybody really cares, as long as you get one copy and you can't distinguish between them. Okay, so that's virtual inheritance. And I will not go into any of this code. This code is available. I will not go into any of this code, but I want you to see it. So account is my superclass. You got it? Then I'm going to have implementation of account. Okay. Then I'm going to have a free checking account. Public virtual account. Get it? So again, how does it affect free checking? It doesn't at all. It doesn't, because this only has to do with further subclasses of free checking, not free checking itself. So free checking is a virtual of account, free checking. Then we have joint account, public virtual account. So we have account, free checking, and then joint account. So now free checking and joint account, we're going to create a diamond inheritance. We're going to create a free joint checking. So here it is. Look at this. Class JTFR checking, public joint account, comma, public free checking. You understand? Closes the diamond, but only gets one copy of what? One copy of the account stuff. What does that mean? Only one account balance. Probably a good idea. Could you imagine having two account balances? Like you always add to one balance and then the other computer programmer wrote, you subtract from another one. I mean, that's a problem. Or you deposit and you check your balance, it's still the same. Or you withdraw, well, that might be good. Still the same, but you know it's wrong. Okay, so. This is the display method from joint free checking account, right? That's an override. Joint free checking display, right? Look what I'm doing in it. In this code, I'm calling display. So do you see what I'm doing here? I am calling my superclass display method. What's another one I can call? Free checking display. So this is display in the at the bottom of the diamond, and this is the display on this one. Remember, this is not double inherited because this is only an override from here. Okay, next I'm going to cover a little bit is I'm going to talk about, we already talked about templates. I want to show you some simple example of templates. Okay? Simple example of templates because they're important. If you understand the simple templates, then the STL stuff will become even more obvious or simple to understand. So the first thing I have is, so this looks like a normal top level function, right? If you get rid of template and you get rid of class T and you change T to int, you have void swap int by reference A, int by reference B. So basically, what we're saying is this is not a function int by reference A, int by reference B. It's a function where you can take two things of whatever type you like by reference. So class T means that T will be replaced by the template generator to actual types. So how do you swap things? Well, basically, if you're swapping things of type T, you need to have a temporary T. Right? If I want to swap two things, two ints, I need a temporary int. With this. So T temp gets the value of A. A then gets the value of B, and then B gets temp. That makes sense, right? So it's an exchange. But again, this is a template for a function. It's not a function. It doesn't get created into actual source code until the compiler sees a call to swap. And of course, a call to swap finds it here, finds it here, finds it here. So when the compiler first finds swap ij, it says, what is I? Int. What is j? Int. So therefore, it uses int as the t-value, and it creates void swap int reference A, int reference B. Int t equals A equals B equals 10, goodbye. So it generates a function where this goes away, int, int. And that's your code. And it works. So now, the compilers, so basically, that generates one version of the function, int, int. I'm using int, int here, right? Int, int. Next call, it sees DE. It says, okay, what's D? D is a double, E is a double. So guess what? It replaces T with double. It creates double reference A, double reference B, double temp. Creates another source code, second version by the generator. Then it says swap S1, S2. It says, what's S1, S2? Well, S1 is a char pointer. What's S2? It's a char pointer. So it creates another function where T becomes char pointer. Void swap char pointer by reference A, char pointer by reference B, char pointer temp equals A. This char pointer goes into this char pointer. This char pointer gets that char pointer. And then this char pointer gets the copy of the temp. Get it? So how many codes are generated out of this template? 3 functions. 3 functions are generated. Is that complicated or is it kind of simple? Not too bad, right? So this is a single function, but again, we can template a whole class. Like what? Like vector, which is STL. But this is not STL. This is actually our own, right? Let's look at another example. So let's say we're trying to do a binary search. Do you remember how binary search works? Do you remember it? So we have an array. We're going to find in the middle. We're going to say, are you a match? No. So what I'm looking for is smaller. Okay, so in that case, binary search here. If it's bigger, then binary search here. And then recursively go to this binary search. We find the middle. Is it a match? No. Is it less than? So we keep cutting this array in half, in half, in half, in half, in half. Very efficient because we can only cut something in half. How many times? Log base 2 of n. Like 16. 8, 4, 2, 1. Log 2 of 16 is 4. 32? 16, 8, 4, 2, 1. 5 times. Log 2 of 32? 5. 1024? 10 times. A meg, which is about 1,000,000, 20 times. So forget about template, forget about class K, forget about all this. Think that you have an array of something, you're searching for the key, and this is how many elements you have. Okay? So what we're going to have is we're going to say the left index is 0, the right index is end, and then we're going to have a mid index. While left is less than or equal to right. While less than is less than or equal to right. If it's less than or equal to right, we have at least one element. Mid is equal to left plus right over 2. Find the middle. If the key is bigger than the middle, then we want to make left right of the middle. Else, if the key is left than the middle, we want to make the right left of the middle. Else means it's not greater than, it's not less than, it's a match, so return A plus mid. A is the address of the array, plus mid is the address of the matching element. We will continue doing that. So basically we start here and here, we find the middle. Okay, if it's not a match, we're going to go either to the left part or the right part. Huh? Get the idea? So this works. Now, we are making a template out of this function. So rather than that being a function for searching for a key of type int in an array of int. I can search for a double in an array of double, which would be a different function. I could search for a rational in an array of rational. I can search for a num in an array of num. I can search for whatever in an array of whatever. So it's kind of like void pointers, but templates do it a little bit more elegantly. So in this case, I'm creating a template for class K where I will search an array of anything for a key of that same type, and I will return a pointer to the matching element or null if it's not there. Okay, so you see what the function looks like. So the function, so basically what type is key? Key is of type K. K greater than K. Now L is just unsigned int, so that's fine. K less than K. Return K star plus int. So it will return a K star. So K star plus int is a K star. What's K? I don't know. So now to use this, what I'm going to do is, so now I'm going to have allows compare. Now in this case, what I can do is I can also try to create a template of two classes, K and L, where I'm looking at an array. Okay, so in this case, I'm looking at an array, and so it gets a little more complicated because now I'm putting functional pointers in here. So I don't want to mess it up too much. But the idea here is that we can easily implement this. So all I have to do is have an array of int and do a bin search for a particular value for this array and send the number of elements and it will return correctly. Now, if I have an array of int, if I send int, array of int 25, it works. If I have double, array of double 25, it works. If I have rational, array of rational 25, it should work, but it might not work if I don't have this operator defined or this operator defined against rationals. So the template generator will generate code, but you have to make sure that if you're using your own classes, that those operators are defined for your types so that the code can actually go through the compiler successfully. The template generator can generate code which will not compile, because it doesn't know what methods and operators you have defined for your classes. So, I'm skipping. So many notes. I think we have enough. I'm not going to kill you with this. Okay. So now we're going to go to, I want to go into, I'm not so much, I'm going to sort of shy away a little bit from those offset pointers to members and member functions, because they're just basically functional pointers and pointers, but they are restricted to classes. And we saw enough about it last time that you get the idea that you can have it. So not only can you have a pointer to a function that takes two ints and return void, you can have a pointer to a function from this class which takes two ints and returns void. So you can specialize it. All you have to do is put the class : and then the functional pointer. And we saw that a little bit last time, so I'm not going to worry too much about it. Okay, so let's go to the last topic that we're going to really cover in the class, and that is going to be it's going to be design patterns. If I get the first one here. Okay. So let's talk a little bit about what design. How many of you have heard of design patterns? Raise your hand if you've heard of design patterns. 1.5 persons or half a person. Okay. Design patterns are techniques for programmers to write the type of code that tends to be needed more than one time or oftentimes. Somebody gives you a problem they want you to solve, and you say, okay, and you put a lot of effort into it, and you reinvent something very exciting, and they say, okay, now solve another problem. And you spend a lot of time, and you reinvent or invent an idea, and you implement it, and it works, and then somebody else says another problem. And all of a sudden you say, wait a second, that's the same problem I solved the first time and the second time. You're asking me to do it again. I get it. There's a pattern here. There's a repetition here. I'm doing the same thing over and over again. For example, let's say we wanted the following behavior in a program. And the behavior is, I want to create an object of some class. Right now it's class A, but tomorrow it might be class B or D. But I want to create a class, an instance of class A in such a way that if one doesn't exist, I don't have one. But if somebody wants one, I'll let you construct it. But if you want access to the object and it's already existing, I'm going to give you the pointer to the existing objects. I'm not going to construct another one. In fact, I want only one copy of this object in the program, or 0. So 0 if nobody needs one, but if somebody needs one, I will create one. If you want one too, I will reuse the same one and give you a pointer to it. So that might make sense if that one object, for example, is going to have access to, for example, maybe a socket or some internet connection. You don't want to have 10,000 of them being created. You want to create one and then just reuse it. This type of pattern is called a singleton. A singleton pattern basically says, I want you to create only at most one copy of an object and use it to whomever wants to access it, use it. So if somebody tells you this problem, you're going to go, how am I going to do that? I mean, what if somebody says new A, I got 2 A's. So you can't allow them to say new A. Oh, how am I going to solve that problem? Well, the constructor is public, I'm going to make it private. Now nobody can say new A at all because now it's private. Now you can't have any A's. So that's too much restriction. One is not enough restriction. That's a design pattern problem. Or somebody says you can create 3 objects, 0, 1, 2, or 3. But if somebody wants the 4th one, reuse one of those 3. So that's a general, more general, instead of a singleton, an Nlton. So we own n copies of it at most. You get the idea. So design patterns are things that we tend to solve over and over again, and if we can see what it is, we can perhaps more quickly adapt a problem. So this is just some notes, a generally repeatable solution. It's not a finished design that can be transformed directly. It's a description or a template, different word template. It's like a recipe, right? Recipe, how to solve a problem that can be used in many different situations. So that's what a design pattern is. It's like an approach, a set of solution steps. Design patterns capture experience of expert software developers and present common recurring problems, their solutions, and the consequences of these solutions in an organized way. Lack of experience or guidance can lead to too many objects with too many interactions and therefore dependencies. Okay? So this can defeat the problem of object-oriented design because it's going to slow it down too much. So design patterns help overcome problems like this because they teach the lessons which are distilled from expert experience. Patterns document experience. Patterns not only describe how software is structured, but more importantly, they describe how classes and objects interact. For example, let's say you want to have a program, and the program is going to be taking graphic user interface. It's going to be taking a GUI, right? So we might have, for example, a button, many buttons, but let's say when this button is pressed, something is going to happen. You press OK or whatever. Well, I want not only when something is pressed for something to happen in the program logically, I also am waiting for this button to be pressed because when this button is pressed, maybe the first time, I would like a whole set of activities to happen. I would like to create a log, I would like to open a file, blah, blah, blah. So somebody is listening for that event, and we call that type of a listener an observer. So it's like somebody basically like, no, button is not pressed yet. No, button is not pressed yet. No, button is not pressed. All of a sudden, oh, button is pressed. Okay, start cruising. So we want an observer. So an observer is a kind of a role that happens in some of our design patterns, an observer. So we want something to happen. The observer is just dedicated to just looking and waiting for something to happen. Okay? Another example of a pattern will be something called a proxy. Have you heard of proxies? You've heard of proxy servers, right? What's a proxy server? A proxy server could be somebody who acts on your behalf to do something for you. It's a level of indirections. You also may have some cases you want to have, let's say you want to have an object, and I only want this object to be accessed 13 times. You can create as many as you want. But I only want you to access a particular method 13 times. So if you have an object and you access a different method 100 times, okay. But then when you access this one special method, I want to say 1. And if you want to access it 10 more times, I'm going to say 11. And somebody else creates it, they access it 12. And somebody else creates a new one and says 13. And when I access this method, no. This method is not going to give me what I want now. So that's another pattern. How do you do that? It's reasonable to have that as a design criterion. It's reasonable to have that as a requirement, right? You can only access a particular behavior this many times. I don't know why. Maybe that's because there's a restriction on the resources, right? You've only paid for 13 accesses. So you can make 1 million objects, but only 13 times you can access this particular resource. So I'll count them. So once you try to access it afterwards, I'm going to give you a message. Sorry. Or I'll give you a message, 12 more left, 11 more left. And sorry, you have 0 more uses. That's a design pattern. Now, patterns do not make your code easier. They actually make your code, unfortunately, a little bit more complicated. So you don't, and they, in C++ specifically, they rely tremendously on templates. And that's why we cover them last, because we want to make sure that you know what templates are. When do you not use a pattern? Well, basically, while pattern properly results in reusable code, the consequences often include some costs as well as benefits. Some cost, that's a bad thing. Reusability is often obtained by introducing encapsulation, so we wrap things in other objects, encapsulation. Indirection, we go here, but I send you there, so it complicates things, which can decrease performance and increase complexity. So design pattern implementations sometimes are not the most obvious ones, but they solve certain problems. So if you don't need to solve those problems, maybe you don't need to use design patterns. Use them when they are when the benefits are big and the costs are low. There are 3 groups of design patterns. Creational. Creational means we're trying to create objects. So one of the ones I talked about a minute ago was the singleton pattern. The singleton pattern is a creational pattern. I'm trying to create an object from a class so that only one copy will ever exist, at most. That's a creational example. So that's creation, when you're creating it. And then we're going to look at a few examples. Structural design pattern is when we're trying to put classes together, structure them together, make them interact together. That's a structural design pattern. Okay? And the last one is called the behavioral design pattern. And that means it's a pattern for programming that is going to model the behavior of objects. How do you want the objects to behave or to react? So that has to do specifically with methods, right? How methods are doing, because behavior is methods. Structural is how things are put together. What's my property? What am I referring to? How am I creating this class in correspondence to other classes? So this is an example of the singleton pattern we talked about. So how do we solve this problem? Well, one very easy way to do it is, if I would like to have a class, and I'm going to call it singleton because it's a funny name. And so what I'm going to do is I'm going to create, you see the constructor? You see it? What's different about this constructor?
Same name.
What's different about this constructor? that we've never done before this semester?
Private.
We stuck it in the private section, which means what? Which means that any of the methods here can see it, but nobody else. Clients can't see it, subclasses can't see it. So you can't say new singleton, haha. But what you can do, you can say there is a static method called singleton. It has to be static. Why? Because if it's not static, in order to use a method, I would have to say new singleton. But I can't do that. I can't create a singleton because the constructor is private. But I can call a public static method called singleton, or getInstance rather, which will return to me a pointer to a singleton. So the way I would call this code, I would say singleton dot getInstance. Get it? So I can do that. Why? Because getInstance is static. I can call it from the class. Singleton dot getInstance. And static, so I don't need to have a singleton object. It will return to me a pointer to a singleton object. I can't create one by saying new, but I can try to get a pointer to one from getInstance. So that means that this method is the most important method here, because basically this method can get access to anything private, right? I have a pointer to a singleton, which is called instance, and I have a private constructor, I have a destructor, right? And I have a getInstance static method. If I took away the static method, what would happen? I couldn't call getInstance because if it's not static, I would need a singleton object to call the method. So the only way you can call a method from a class if it is static. Okay, so now, well, that's interesting. I don't have the code for here. So now I have to write the code. I don't like that idea. All right. So what we're going to need to do, the constructor is going to do something like this. Yep. Okay, do you see what the constructor just did? No, I don't want to do that. Yes? I'm going to change it. Okay. So the static value is assigned what? Null. So now some client program is going to say singleton dot getInstance, right? Like that. And that's going to start this method, right? Which I'm putting in line right now just so we can see it. So this method is going to say if instance equal null. Is it equal to null? Yes. It is now, right? Then instance is equal to new singleton see what I just did? So if instance is null, then construct a new singleton. That's going to create a singleton object and put a pointer into instance, which will make instance not null. And then I'm going to say return instance. End of the method. So the first time somebody calls it in a code, instance is going to be null. So therefore, instance will be equal to new singleton. So instance will be connected to what? To a new object, right? And then I will return the pointer to this object. The second time somebody calls it, the next time, instance equal to is false. So it'll just return. That's it. Now, so that's called the singleton pattern. Now, what if I wanted you to modify the singleton pattern and I wanted you to allow up to three copies of the singleton object? Call it a tripleton. How would you modify it if you wanted to have up to 3 copies? What would you have to have?
Can you do locking?
Locking? We don't need locking.
You can't access more than one class at a time.
We first of all, well, what we would need is we would probably need multiple singleton pointers, maybe 3 of them, right? And then you can say if instance is equal to null, or if instance 2 is equal to null, then you can decide to construct another one, return that one. But if none of them are null, then you can return a random one of them, not any one of them. Get the idea? So it'd be easy to modify now, right? Now that you get the idea. So that's an example of a singleton design pattern. But so next time somebody says, I need you to create this project, but I can only have one copy of this object. You don't have to be all like, oh, how am I going to do that? Singleton pattern. Okay? So these are still creational prototypes. Data pattern prototype is very, very interesting. A prototype is a way to create a new object which are copies or clones of existing objects. How many of you know Java language? Have you heard of the clone method? The clone method actually is a prototype data pattern implementation. So a clone method. So the prototype pattern is a creational design used to development with types of objects to create is determined by the prototypical instance used for polymorphic dynamic instantiation. So any class to implement this pattern, declare an abstract base case. Remember what is an abstract base case? That's a base class which has a what kind of method? Pure virtual. Once you have one pure virtual method, you are abstract because nobody can instantiate you. So you create an abstract base class that specifies a pure virtual clone method. Get it? So we put pure virtual clone into the base class. Once it's pure, it's abstract. Any class that needs a polymorphic constructor derives itself from the abstract base class and implements the clone operation. So we create an abstract class, and this abstract class has a pure virtual clone method. And then a subclass of it will override that clone method, which is pure virtual, and they will implement their own virtual actual code. And what will the code do? It will create a replicate of that object. So you can see here is our product is our superclass. Product is our superclass. Nobody can complain now. As big as I can go. And so I have a prototype table. I have a method called make product, add product, and I have clone. Now this method could be real or not, but this method must be pure virtual, making the whole class abstract. And so what happens is when I create product 3, product 2, product 1, which are all subclasses of product, I now have to override and implement this virtual clone method here from this pure virtual. Okay? So look at the example code here. So we have class prototype. notice that it has some protected data. Again, why protected? Because we want this data to be accessible to subclasses, but not to clients. Good. And now public, notice that we have a clone method. It is pure virtual. And what does it return? It returns a pointer to the prototype. Now, it has type and value, and it has real methods too. That's okay. You can have real methods in an abstract class. If you have one abstract method, meaning pure virtual, then the whole class is abstract, even if you have actually nice methods and nice properties. That's fine. They'll get inherited. The nice methods get inherited, and the pure virtual methods get inherited too, so you have to override them in order to make the class not abstract. What's the opposite of abstract? What do we call a class that can be instantiated? Starts with C-O-N-C. C-O-N-C-R. Concrete. Like concrete is like what you make sidewalks from, concrete, right? Solid, concrete, real. Okay, abstract, not real. Okay, so prototype is a superclass with a pure virtual clone method. And now we're going to go to, we're going to subclass this method, right? So this is an abstract base. So here we have concrete 1 and concrete 2. See them? Public prototype. Clone. Notice clone has to return a prototype star, not a concrete 1 star, because otherwise it wouldn't be an override. It has to be exactly the same. And remember, concrete 1 is a prototype. So concrete 1 pointer is a prototype pointer. So it will have, and so here is a clone method. This clone method is public, and it returns new concrete 1 star this. You understand what it's doing? It's constructing one of this based upon itself. So it's calling basically itself. Okay? Any questions? And the same one goes here. So that's a design pattern for prototype. And we can test it. This is a testing right here. So we're going to create an array of 2 pointers to prototype. Remember, prototypes don't exist. Concrete 1s and concrete 2 do, right? So, in this case, we're going to have object array 0 gets new concrete, so we create a concrete 1 instance. We create a concrete 2 instance. Now we're going to take time null. Remember what that does? Number of milliseconds since January 1st, 1970. SRAND seats the random number generator, and then we'll randomize the number rand integer modulo 2, so we're going to get 0 or 1. Which one? I don't know. I'm not a genius, I don't know. So the first thing I'm going to do is I'm going to say object array sub I, that means 0 or 1, clone into object. Get that? What is object? It's a pointer to prototype. So I'm cloning either a concrete 1 or a concrete 2, and I'm putting it into object. Then I say object array 0 print, object array 1 print. What will print? Which method? Concrete 1. What will print here? Concrete 2. What will print here? Either concrete 1 or concrete 2 method. Because I don't know what the value of this rand was, right? Get the idea? So this is polymorphism again, right? And this is how cloning works. So cloning works very nice like that. All right. By the way, you might, so this is a great question I could ask you on a final exam. This is especially for graduate students that want to get A pluses on their exams. I could say, what is this right here? What is this code? Constructor. That's the undergraduate question. Now the graduate question is, what am I doing here? I'm calling a what? What am I, is this a constructor? What type is star this? So star this is concrete 1. Do you see a concrete 1 constructor? Yes or no? No. You do not see concrete 1. This is a concrete 1 in constructor. But I'm calling concrete 1 concrete constructor. Do you see that in this class? No. So why is this working? That's the graduate question. Which I also answered, I'm going to say, roughly speaking, in March 12th lecture. Why is this working? Obi? What's the answer?
I don't have this one.
Come on, somebody. This is only for people who would like to get an A in the class. So if you don't want to get an A, don't answer that question.
Default constructor.
Go ahead.
Default constructor.
You're halfway there. It's not a default constructor.
Copy constructor.
So the copy constructor is provided automatically. Unless you override it, and then you can create your own. Now, the question that I want to ask is, what the heck does the concrete constructor do? What it does, it creates a new object, and it assigns all the same properties into the new object properties. As long as the properties are not pointers to external memory in the heap, you're fine with that default constructor. But if your object contains a pointer to an array, and you clone it like this, you will have two objects that will both point to the same array, because their pointers will be copied into the same array. So if you have dynamic allocation and you do the clone method, you're going to have to do what? You're going to have to allocate a new buffer as part, you're going to have to override the default copy constructor. Who understood what I said? No? Did you understand what I said? Not exactly. Okay. Oh, fair enough, fair enough. If he doesn't understand it, and he doesn't understand it, and he doesn't understand it, nobody understands it, right? This is only the place for the smarter students only can sit on this side. That's why I assigned you guys to sit over there, right? So, the copy constructor is automatically provided by C++. I mentioned that in the beginning of the class a couple months ago. So let's say I have a class object looks like this. So this object has, let's say it has an x value is equal to 6 and a y value is equal to 7. Okay? And I want to copy construct this object. So let's say this is an object of type A. So A is an A, right? So I can say something like new A. So new A will construct the new object, and the copy constructor by default will create all the same fields and put all, and copies the values, and it will return a pointer to it. So now I have two objects. So that's kind of what we're doing here. That's a default behavior. But if, for example, this A object not only had an x and a y, let's say in values, but also had, for example, a char pointer to the word hello with a null terminator, okay, and let's call it s, then this copy constructor, which is default, would give me s and would copy the same value s has, which, by the way, is the address to the h. So that's what the copy constructor would do if you had external memory referenced from your object. So it's not, so we call this a shallow copy. because they're sharing some stuff. You want them to be completely independent. So this, you could see this is a problem in some cases. In some cases it could be a problem, in some cases you like it. Most of the time you don't like it. What you want is you want the copy constructor to allocate a buffer the length of this and do this. You get it? So when this object is destroyed and it takes this buffer with it, this one is still not pointing at this memory, which is gone, back in the heap. Okay? Make sense? So if you wanted this behavior, you would have to code your own copy constructor, which would be concrete one, reference, blah, blah, blah. And you would have to copy, copy, copy. Your pointer is equal to new allocation of the buffer, copy, 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 goodbye. So in this case, we're okay because if you notice our prototype only had a string and an int, and those can be copied for the most part. All right, so that's what we have here. All right, so let's take a look at another pattern. This is the last creational pattern that I'm going to look at, and this creational pattern is called a builder pattern. We're trying to build something. We're trying to build something. So this one is a little more complicated because the builder pattern has four main parts. A builder, a concrete builder. Well, that means that the builder is abstract. Again, what does that mean? Pure virtual, at least one pure virtual method. So the builder is going to be abstract. The concrete builder will extend builder and realize the pure virtual methods. We have to have a director, and we have to have a product. So the builder is an interface, which is also known in C++ as an abstract class. The product object is the object that gets assembled in the builder pattern. Concrete builders implement the builder abstract class, and they are responsible for the directions of what to do. What does a director do? Well, what do you think a director does? A director is responsible for constructing the product. It does this by calling the director doesn't actually do anything. It tells other people what to do. That's what a director does. That's a good name, director. Let's look at an example. So let's say the product parts we have the following product parts. So we have a wheel. Don't you wish the whole class was like this? You have one property here. Then you could all get A's right now. So a wheel has public size, has an engine, has an int horsepower public, and a body string shape. All right, so wheel, engine, and body are the products. These are the possible products that we have, product parts. So now what we want is we want to have a product that's going to be a car. So the car is going to consist of an array of four wheels. A lot of cars have four wheels. It makes them much more balanced than the three-wheel cars. They do have an engine, and they have a body. And the print method will basically do what? It will just output all the interesting things about this car, the unique things about this car. So a car is made out of an array of wheels, a pointer to an engine, and a pointer to a body, which are these parts. So now we're going to get a virtual builder. That's where we have our virtuality. That's where we have our pure virtual methods. So the methods is to create a car, you have to actually get a wheel, get an engine, get a body. But because it's a virtual builder, in the builder design pattern, the builder will actually not implement these methods. It says, okay, if you want to get a wheel, I will return to you a pointer to a wheel and a pointer to an engine here and a pointer to a body. But I'm not going to do it. If you want to do it, you do it. And the reason you're doing it is because you're trying to create different products. So different specific concrete builders will do this job differently. So now we're going to have a director. But before I even have a director, I'm going to jump down here and I'm going to show you a concrete builder. So the concrete builder is a subclass of the builder. So you can see Jeep builder is a builder. And notice that get wheel, get engine, and get body are implemented. That's an override of the pure virtual. They're still virtual, but they're not pure. They are now coded. So if you want to get a wheel, if it's a Jeep, then I'm going to construct a wheel object, which is nice. I'm going to set the size to 22 inches, and I'm going to return the wheel. If you want to build a Jeep engine, I'm going to set the horsepower to this of this engine that I'm going to construct. I'm going to return it. If you want to build a body, I'm going to create the body, and I'm going to set the value of that to SUV. Is that clear? Now, if you want to build a Nissan, it's also a public builder subclass. So the wheel is a different size, the horsepower is a different size, and the model is a different size. So you see these are concrete builders. They're implementing the builder interface. And so now we also will have the director. So the director tells you what to do. So for example, here we have the class director, and the director has a pointer to a builder. What's a builder? A builder is a Jeep builder, or a Nissan builder, or a Ford builder, or a Porsche builder, or a Cadillac builder, right? Mazda builder, whatever. Those are all the concretes. So the director has an access to a builder. Remember, I told you, the director doesn't actually do anything, but it tells other people what to do, so it needs to have a builder. What kind of builder? Any kind of builder, because a builder is pure virtual superclass. This builder could be talking about a Jeep builder or a Nissan builder, right? So the constructor for the director says basically, or not the constructor, but we have a method called set builder. Set builder basically gives you a builder pointer, and we set our builder to this one. So somebody could say set builder and give me a Nissan builder, or set builder give me a Jeep builder. So when somebody has a director, they're going to set the builder, and they're going to say, okay, now give me a car. I'm going to give you a Jeep builder, get me a car. So the director is going to construct a new car object, and then it's going to customize the car. It's going to basically say, okay, builder, what kind of builder are you? I don't know, I'm a director. Hey, builder, hey, give me a body. So it gives a Jeep body. Give me an engine, gives a Jeep engine. Give me a wheel, give me a wheel, give me a wheel, give me a wheel. Jeep, 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 Jeep. Return car. So notice the director has a builder, which it doesn't know what kind of builder it is, because it could be any of the subclass of the abstract builders. And then it tells the builder, when it's time to get a car, it constructs the car, and then it basically puts into the body of the car and the engine and the wheels whatever the builder provides. So if the builder is a Jeep builder, it will assemble a car with Jeep parts. If it's a Nissan, it's going to assemble a car with Nissan parts. So in the example of this design pattern, we have a car pointer, and we create a director by default constructor. We create a Jeep builder and a Nissan builder by default construction. So then I say cout Jeep, and then I say director, set builder, and I give it a pointer to the Jeep builder. And I guess the reason it's a pointer is because, whoops, when I can set builder, they want a pointer. Why do I want a pointer? Why pointer? Why not just pass the builder? Cannot pass just builder, because by value you lose polymorphism. Because remember, when the builder get body, it could be a Jeep body, Nissan body, Ford body, right? That's so different methods. So that's late binding, isn't it? The only way you get late binding if your builder is passed by pointer or by reference. That's the only way. And that's why we do it that way. Okay, so you can see here, so I'm passing the address of the Jeep builder, which is a Jeep builder pointer, which is a builder. And then once I set the type of builder to the director, then I ask the director to get a car. And of course the director then tick, 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 returns the car, and that goes into car, and I print the car. And on the next try, I basically take the same director, I set the builder to the address of the Nissan builder that I created here, and I say get car, and I print the car. So this is the builder pattern. Other patterns are called factory patterns and abstract factory patterns. These are still creational patterns. Factories allow you to build things that you can customize, and abstract factories allow you to build things that you don't even know what you're building, but you know the process of building it. So I can just go quickly here. So let's say we have an abstract base class. So we have a class called smartphone. It's an abstract base because it's pure virtual here. So print specs will print all of the internet speed, the camera, and the keyboard, but none of these things are going to be actually implemented. So we have an abstract base. And then we have actual phones. So smartphones is a cheap smartphone and a fancy smartphone. We just have two different kinds, right? And so what you can have, you can clearly see that these virtual methods are implemented, right? So one set of information, and for the fancy smartphones, another information, right? Okay, so you get the idea. So far we have smartphone, virtual base class, and then we have cheap and fancy smartphones, concrete subclasses. So now we're going to create something called a smartphone factory. So smartphone factory, so here is get smartphone. So if you say get smartphone and you say what you want, I will return to you a smartphone. But in reality, I might be returning a cheap smartphone pointer, or another time I may be returning a fancy smartphone pointer. So here is the method here, smartphone. So this is the implementation, right? So I'm going to send in a string, and the string is going to be called the type. If the type is equal to cheap, then I return a new cheap phone, which is a smartphone. And if it's fancy, then I'm going to return a fancy phone, which is also a smartphone. So that's called class factory. So basically the factory, based upon some input, decides what to construct, and it returns, okay. If, by the way, you give me something that's not cheap or fancy, I will return null because it means I don't know how to make that. So that's a factory. And it's a test. And the final example here on the creational patterns are so-called abstract factory pattern. Abstract factory pattern. So similar to the factory pattern, the difference being that the factory itself is abstract. So you have to first get an appropriate concrete factory before creating objects. So rather than the factory being concrete, the factory itself is an abstraction. So we can look at this example here. So let's say we have a class called widget, which is abstract, and then we have motif widget or motif menu, which are widgets, and Windows widgets and Windows menu, which are also widgets. So I create 4 widget concrete subclasses out of the widget abstract class. So the only thing that we're going to have is a method in the widget. What's a widget? Widget is just a thing. It's a very funny word in English. It's a thing. Widget. We make widgets. What does that mean? I don't know. Things. So you can see the widget has a virtual, has a pure virtual draw, and then all these other motif is kind of like a Unix style button is a widget, and a Unix style menu is a widget, and a Windows button is a widget. So they're all widgets. Notice that they just print some specifics. So then I'm going to do this is just basically using the preprocessor directives. So if somebody pound defines motif or not, it's going to depend. If it's defined, then it's going to go from here to the end if. And if it's defined, it's going to go from here else here to the end if. So it's pound if def motif, it's this, else Windows, it's this, end if, all the same. Okay, so for example, if you look over here, we have the display window 1. So if motif is design, then I'm going to say W is a pointer to widget, which means an array of widgets, initialized to a new motif button and a new motif menu. Else, if motif is not defined, then W is an array of widget pointers with a new Windows button and a new Windows menu. End if means that, so this happens at compilation time, right? So whatever, if you define it. So this is compile time. This is preprocessor time. So the compiler will only see one of this one, or this one. But it could be different for every time I build my project. And then I say W0 draw and W1 draw. Display window 2 looks very, very similar. Again, display window 2. Notice it's, again, the same thing here. Pound L, same thing here. And then draw and draw. So those are going to be these guys right here. And now we can test the preprocessor solution. So for example, if I'm going to define, so I can do a pound define motif in my header file. Also, you can use it in your command to run your program. You can say -d motif. -d motif means that you are defining motif. If you say -d motif, that means the preprocessor will see that it's defined. If you say -d motif equals 7, it will define it as 7. If you say -d motif, it will define it as nothing, but it'll define it. So you can see here the output is going to be motif button, motif button, motif menu, motif menu, motif button. So basically, it was defined. So therefore, because it was defined, it skipped this part of the program. So this is, again, the widget with the abstract value here. The motif button is a widget, this menu is a widget, it's a widget, it's a widget. So now we have two concrete factories. So we're going to create from the factory class. This is going to be a virtual class. So we're going to say basically create button and create button, create menu, and they're both pure virtual. So this is the abstract factory. So the factory is now abstract. It's not, cannot be implemented or instantiated. The motif factory is a subclass of this, so therefore we have to implement or override these pure virtual methods. So here we're going to return a new motif button. Here we're going to create a new motif menu. But the Windows one is another subclass. It will return new Windows menu and return new Windows button. And so if we were going to test it, you can see here, if motif is defined, then factory is equal to new motif factory. Else, if it's not defined, then factory is equal to new Windows factory. So again, I could have done it using a random number generator if I wanted to, this one or that one. I did it with a preprocessor, just to show you that sometimes factory is going to come out with a Windows factory, and sometimes when I run it, it's going to be a motif factory. What's the same about them? They're both factories. They're both concrete factories, subclass from the same superclass abstract factory. And so we're going to come out here and we're going to say widget star W equals factory create button. So when I create button, a button is a widget, I'm going to get it here. When I draw this button, it's going to say what? Windows button. Display window 1, display window 2. Notice that everything is going in the Windows direction. Okay? So that's kind of the idea of the factory and the abstract factory pattern. So all the patterns, design patterns we looked at so far, all of those patterns were creational. The next part of our design patterns we're going to look at is we're going to look at design patterns that are structural. So structural patterns are patterns that allow you to put things together, to build things together in ways that will promote reusing certain concepts that are very, very popular. So One important one that we can have is called the adapter pattern. So adapter is a very simple idea. Think about, like for example, when I had to go to China, I learned that in China they have different power, you know, instead of plug going like this, plug going like this. All right? But some of the computers and some of our electronics can be plugged in. Now, I also learned that they also have to convert the power, because the power in China runs at, was it 200? 220 volts. But power in the US, 110, 115 volts. So when you plug it in, so if the problem is that I cannot plug it into the wall. Even though it's 220, my computer can take it at 220 because it'll convert it automatically. But the problem is if I try to pull it in, it's not going to go in. So what I have to do is I have to put a plug into the Chinese outlet that looks like this. And on the other side is a plug for the US style plug, which looks like this. That's an adapter. So you take something that basically has one kind of interface and you project another type of interface. You adapt it to work in a different situation. So an example of that would be that you have, for example, let's say somebody has written a big important piece of software that works by having, so you can use this software if you connect to a certain method with certain parameters. So you need parameters A, B, C in order to use this. The only problem is that the program that we're going to interface into it does not have parameters A, B, C. It has parameters X and Y. But parameters X and Y can be converted by some function into A, B, C. So what we're going to try to do is we're going to try to wrap around this important ABC function and create an interface for XY so that our project, which is used to using XY parameters, can be adapted to use this one. So it's an adapter pattern. Use something that you expect one type of input and adapt it to a different type of input so it can still be reused. So it's a reuse type of feature. Okay. So the structure looks something like this. We have a client, we have a target, we have an adapter, and then we have an adaptee. So I'll try to explain that a little bit. So the client is basically something is trying to use this. So this is the adapter. The adapter is a subclass of the target. So this is the target, and then the adapter depends on the adaptee. This is the actual class that's going to do something for me. This is the client, and this is the adapter interface and implementation. So let's look at an example. So let's look at a code example where I'm going to have the target be a circle. The adapter is going to be a circle adapter. The adaptee will be a standard circle. So I'm trying to use a standard circle, but I don't have the same interface. And then the client will be the circle object in main. So these are my 4 pieces. So let's take a look at them. So the first thing we're going to have is the standard circle, or the adaptee, is useful. So we want to use it, we want to reuse it in our project, but the interface of the standard circle may not be what we are expecting. The method old draw has the functionality we want, but we need a draw method and a constructor that takes a diameter, not a radius. So we have 2 problems. We want to be able to construct this standard circle, but the constructor takes a diameter and we want to give it a radius. So we want to adapt it so that it can be used. Also, we want the old draw method, but we don't know old draw, we call draw. So we want to adapt it. So here is the standard circle. This is something old, I call it old draw, old circle, because this is something we want to reuse in our current project without having to redo it. Again, this is one class. We could have 50 classes that we're trying to adapt. So this could be very, very important, because this class could be dependent on a bunch of other things, right? So this is the tip of the iceberg. So the standard circle takes a double radius, where it basically says, okay, radius is going to be assigned into my property called radius. and then I'm going to see out standard circle created with radius equals to some value, and the old draw will say standard circle, old draw, and it'll print out the radius. So this is just the standard circle. Okay, now what we want to do is we want to have a class called circle. So we will create circle is going to be our target, and it will also be an abstraction. It will be an abstract target. So class circle is going to be basically have a pure virtual draw method. It's not going to be implemented. So what we're going to try to do is we're going to try to have our client use this interface. An abstract class is like an interface because it basically cannot be instantiated, but it just gives you the pattern. And the pattern is this one right here. So now we're going to create the actual adapter. So the adapter will implement this new interface. And so circle adapter is a subclass of the circle, and notice it's also a private of the, so this is very, very nice, because what's going to happen here, the circle adapter is a circle. It's going to override the method draw, but it's also going to have access to the standard circle without passing it forward. So this is a combination of an is-a-as-a inheritance. That's very, very nice. So the circle adapter is going to basically allow you to construct through the circle adapter a circle, and you can pass me a diameter. And when I pass the diameter, what I'm going to do is I'm going to go to the standard circle, which is me, right? That's also my subclass, superclass. And I'm going to pass in the radius. So it's going to construct the standard circle. As you construct the circle adapter, I'm going to construct for you the standard circle. And it's going to say circle adapter create diameter equals, and print out the diameter. And now we're going to have the method draw. Notice I say virtual here. I don't have to say virtual. And the reason I don't is because that method is being inherited as a pure virtual from the circle. It's already pure virtual. So even if I don't say virtual here, it's virtual. If I say virtual, it's okay, but it's not necessary. So it's a virtual method, and I'm going to say basically circle adapter draw. And then what I'm going to do, so when somebody calls draw, what am I going to do? I'm going to call old draw. So the circle adapter will present the standard circle to the client as a circle. The circle adapter will present to the client the standard circle, okay? The standard circle as a circle. That's what we have here. So let's test it. So we are going to create a circle, pointer, C, equals new circle adapter 100. So what's going to happen here? It's going to call the circle adapter with 100 being the diameter. This one will construct a standard circle, which is hidden inside here. It will create a standard circle with a radius of 50. And then it's going to tell this circle is now going to draw. So when you call draw, what's going to happen? When you call draw, it's going to call old draw from this one. So as far as the client is concerned, this is now the client, right? It's the client. The client constructs a pointer to a circle, uses the adapter, and then uses the interface in the circle to interact with the standard circle. Notice that the client is not even aware of the existence of the standard circle. So that's an adapter. Another very famous pattern is called the facade pattern. Does anybody know what the word facade means? Facade basically comes like very similar from the word face, right? From facade. A facade is just the front of something. The facade. Somebody who makes a facade, they can look happy, but maybe they're not happy inside. Or they look sad, but maybe they're not really sad. Just a facade. So it's a front. It's not the real thing. It's just a front. So sometimes the facade allows us to do things like project something that that's a little bit different than what's actually there. That's what we're talking about. So the facade pattern has three participating classes. The subsystems, which are in here, the client, and the facade class. So the client will be connecting with the facade to get access to the subsystems. That's the idea. A facade is an API. What's that mean? Application Program Interface. So it's an interface for clients that want to interact with something hidden. These are hidden, and the client wants to interact with them, but the facade is going to make that happen for us. So the classes in this facade include customer service, which allows the client to indirectly communicate or make requests to the order, fulfillment, billing, and shipping departments. So you can see here is the facade, and this is order fulfillment. That's when you're going to fulfill your order. That's when you're going to have billing. That's when you're going to have shipping. And the facade is in between. It's the client wants to use it. So let's look at the facade pattern. So we're going to create a class called engine and headlights. So these are the engine and headlights are going to be the subsystems. So that means they're going to be in here. Okay, they're going to be in here. So that's where the engine and headlights. And you can see again, very, very simple. The engine just has a start method, and the headlights have a turn on method. I guess I could probably have a turn off method, but I don't. And you can add that in. Okay, so these are the two classes in the subsystem. Now, the car is the facade. So if you think about it, your car, you get into your car, you don't really touch the engine normally, right? You don't actually go in and connect the wires to the light bulbs normally, or take light bulbs in and out, right? So therefore, but you still interact with those systems, right? So when you are pushing a lever, all of a sudden your gasoline pops open, your gasoline fill area. That's another subsystem. So the car allows you to interact with these systems, but you're not really interacting with them directly. You're interacting with them through the car facade. So the car basically has properties that are engine and headlights. And so when you say turn ignition key on or turn ignition key on, so you're starting the car, what typically happens? The headlights turn on and the engine starts. So you see what happens? So you turn the key, but turning the key turns on the lights and starts the engine. So the car acts like a facade. Okay? So in here, basically what happens is we create a car object and we say turn ignition key on, and what happens? The engine is running and the lights are on. So it has the facade of the car has allowed us to interact with those systems. Now, this one here is called the composite pattern. I'm not going to really talk about this too much. It's pretty straightforward. Basically what it is a composite pattern allows one class to have multiple interfaces or realizations of multiple interfaces. Okay? So here we have a component, and here we have a leaf component, and here we have a composite component, where we can have one of these can have one of these, and one of these can have multiple versions of these components. And so in this so I'm going to kind of skip this one because it's just an example. And the last one I'm going to talk about in terms, that's a very important one in terms of structural patterns, is a proxy pattern. How many people know a proxy? So we talked about proxy before. You know, what is a proxy server? You probably heard of that one, right? Proxy server. So a proxy generally is something that acts on your behalf. If you're a very important person and you don't want to go to an important meeting, you send a proxy. Proxy is somebody that you give them authority to act on your behalf. So they are your agent proxy. This is one example. So what we have here is we have a client, then we have a proxy, and a proxy has access to the real subject, okay? So I'll show you an example of that. So the subject is the interface implemented by real subject. So this is the abstract, this is the real. Subject is the interface implemented by the real subject, representing its services. The interface must be implemented by the proxy so that the proxy can be used any location the real subject can be used. So the proxy acts as the real subject. The proxy maintains a reference that allows the proxy to access the real subject. The proxy is used in place of the real subject. It controls access to the real subject and may be responsible for creation and deletion. And the real subject is the object which the proxy represents. So I will show you there are 4 or 5 different classes that have to do with proxies. One of them is called virtual proxies, one is called remote proxies, one is called protection proxies, and one is called smart references. So I mentioned one of these already before today, for smart references. So basically, let's say we want to have a sophisticated access to certain objects, such as tracking the number of references to an object and denying access if a certain number has been reached. So that's an example of a smart reference. So smart reference. How can I limit the number of references that you can have to a particular object? Well, the answer is we're going to use the proxy design pattern. What we're going to do is we're going to take the object here. That's the real object. And we're going to wrap this into another class. We're going to embed it. We're going to keep this here. So my access will be through here. I think I'm accessing this one, but I'm actually accessing the proxy. So the proxy will say, number 1, okay. Number 2, okay. Number 11, okay. Number 12, okay. Number 13, okay. Number 14, no. So that's how we can have the proxy controller. Another one is called a remote proxy. A remote proxy is a local representation for an object that is in a different address space. So for example, if you have an object that's running on this machine, and I'm running another application on this machine, so I could have a proxy here that acts like an agent for this object. So if I want this one to do something, I tell the proxy, hey, add these 2 numbers. This one communicates, this one adds the 2 numbers, returns the value, and then the proxy gives me the result. So I am simplifying the inter-network communication between 2 machines using a proxy. So that's called sometimes a remote proxy because it's acting as an agent for a remote object. Virtual proxies can delay the creation and initialization of expensive objects until needed, where these objects are created on demand. For example, creating a real subject only when do something method is involved. For example, let's say we have a very expensive object. It takes a long time to create it, a long time to create stuff. So for example, and sometimes people say, I want a new one of these. But then for a long time they don't use it, or sometimes they run the program, they never use it. So if somebody says new this object, what I'm going to do is I'm not going to create anything for you. I'm going to give you a reference to something, to a proxy. So you think you have one of these? No. You have a reference to a proxy. And if you never say do something or invoke a special method, guess what? I'm never going to construct it. But if you need to have a method on this object that's important to you, and you say, okay, do something, then what I'm going to do, as a proxy, I'm going to create a real one, I'm going to call the method, and I'm going to send you the results back. So as far as you're concerned, that object was always there, but it was actually created on demand when you needed it. And that's called a proxy. So proxy is kind of like, here's the client, here's the real thing, here's the proxy. Sometimes the proxy goes across the network, sometimes the proxy is just delaying the construction of this thing. So it can basically do whatever you want it to do on behalf of the real object. If you create your program in a very clever way, the client might never know that she's operating with a proxy. She thinks she's operating with an actual object because the behavior is exactly the same as if it was a real object. But you're tracking things, you're networking things, you're delaying construction of certain things, okay? That's the idea. So I'll give you an example of a proxy pattern. So I try to keep it nice and simple, because everybody likes simple. So here is class called subject. So this is what kind of class?
Abstract.
Abstract class. How do you know?
Pure
Because
virtual.
pure virtual method. Okay, so it's an abstract class. So subject cannot be instantiated. But the real subject is subclassing subject. And what we're going to do is the execute method just prints out a string. What's a string? It's whatever I construct the object with. So it's a very simple idea. So you have the real subject, which extends the subject abstract class, implements the execute method to print a string, and the constructor can print the string. So what we're going to do, the proxy subject, is a class that extends subject. Okay, so we have the real subject, and then we have the proxy subject. Get the idea? So we have subject, real subject, and then we have the proxy subject, which is also a subject. So the proxy subject here, very confusing looking, so don't try to figure it out, chops up a string by removing the first three words and then constructs a real subject with the rest. It also overloads the pointer operator. That's what it does. Okay, so here is the proxy subject class, subclass of subject. Here is the destructor, and here's the overloaded pointer operator. It says operator pointer returns a real subject pointer. And here's the void method, execute. So it takes cout first, space, and third. And then it says ptr execute. So you can see that the proxy subject has access to the real subject. The proxy subject has access to the real subject. How? By having a pointer. So when you construct a proxy subject, what's going to happen? So when you construct a proxy subject, look what happens. It basically starts processing some substring stuff, and then it says ptr equals to new real subject s. So when you construct the proxy subject, it creates ptr, which is a real subject. And when somebody says the pointer operator, it returns the pointer. What's the pointer? The pointer is the pointer to the real subject. And when somebody says execute, it executes on. So what's going on is the proxy subject is actually executing. When you say it, you think you're executing on the proxy, but actually you're executing. It's executing on the real subject. So it acts like the interface between them. Okay, so let's test this one right here. So we're going to say, so for example, we're going to say, so proxy subject obj, okay, and we're going to have a constructor is a string. The quick brown fox jumped over the dog. So we're going to create this string. Remember, it's going to take out the first three words. It's going to change the string, and then I'm going to say obj execute. So what's going to happen in obj execute? What's the execute method going to do? Well, take a look over here. So we have proxy subject obj, right? So proxy subject obj means that we are doing this one and we're passing in the string object, right? So it's doing all these things here. I'm just going to stuff them in here, and then it's going to say ptr, which is my local pointer to the real subject, is going to be new real subject with s, where s has already been substring. So it pre-processes this, right? So now, by the time I do this has already been pre-processed and the real subject has been created. So when I execute, what happens? When I execute, it's going to output the first and the third. What's first and third? First and third is the first word and the third word, which already have been taken out. And then it says ptr execute, which means it's going to the real subject and calling the real subject execute method. which is what? Which is outputting the string. So what's going to happen is, the output is, the brown fox jumped over the dog, and then what's going to happen here? Notice it switched the words. So again, so the proxy is able to go in between the client and the real subject or the real object. In between. Always proxy works this way. Okay. Next one is the bridge pattern. I'm going to skip the bridge pattern because I'm going to go to the last one. I am going to go to the last section of design patterns, and that's going to deal with behavioral patterns. So behavioral patterns have to do how methods execute in designing programs. Okay, so far we talked about creational patterns like singleton. What else?
Clone.
Can't hear it.
Clone.
Clone, yeah. Anything else? So singleton, clone, what's another creational pattern we have? Factory, abstract factory. What else do we have? We did another one. Builder. Okay, so review them so when I come up on the test, you're like, oh, I never heard of that. Review them. Okay, so design patterns. So basically, behavioral patterns are patterns of how methods execute, the order of execution, which method executes. Okay, so you don't want to have to think about it. So one very nice pattern, I think, that describes this whole idea of behavioral patterns is called chain of responsibility. Chain of responsibility. So basically, the chain of responsibility describes how we handle a single request using a chain of multiple handlers. So one request comes in, and then how is it being handled? The request has to be processed by only one handler object from this chain. However, the determination of processing the request is decided by the current handler. If the current handler object is able to process the request, then the request will be handled in the process current handler. Otherwise, the current handler object needs to shirk or pass responsibility and push the request to the next handler. And so on and so forth until the request is processed. So it looks kind of like this. So here is the client. The client basically wants something to be done. So it basically, so it depends. This is called depends on the handler. These are actually the actual handlers. So these are the handler 1, handler 2, handler 3. So this issues a request. The request can then be accessed by this handler. If the handler does not handle it, it has to be passed to this handler. If the handler, for example, handles it, then this is the end of the request. The request has been handled. But if this one doesn't handle it, then it has to pass this request to this handler. Sometimes these handlers will go into a cycle. Maybe they're too busy, too busy, too busy, too busy, too busy, too busy, not too busy, handle it. So sometimes these handlers have equal abilities to handle all the requests. In some cases, this one may only handle low-level requests, middle-level requests, and high-level requests. If that's the case, if a high-level request comes in, then this may pass it to this one, but if it's still not high-level enough, it may have to pass it on to this one, and it's going to get handled here. So you always try to handle things as early as possible, and so they will only go further out. So sometimes these handlers are peers, equal level, peers, equal level. Or sometimes they are increasing in their responsibilities. Okay. So that's what I'm talking about. Sometimes the links are peers, and other times they are in the least to most authorized. So let's look at the example of peers. So we're going to look at the example of peers. So the first thing we're going to create is we're going to create the base class. So we're going to call this base class base. And base has a pointer to another one of itself. Okay? And so when you construct the base, it sets the next to null. And then set next, it can point to another base object. So in that case, next goes to n. So by default construction, it goes to null, but I can set it to something else if I want to. So that means that one of these things can point to another one, or it could be null. So I could point here, and this one could be null. That's what I'm talking about. Okay, so you can see that right there. If I have a base and I want to add, and I give you a pointer to another base, I say if next is true, the next pointer add n, else next is equal to n. So that's an important method right here. Let's figure this one out here. So this is the add method. So we want to add from a base, we want to add another base pointer. So we're going to check if next. Next means next is true. If next is true, it means what? That the next has is not null. If it's not null, then go to next, point add n. So what we're doing is we're basically saying, if you want me to add something and I have another one, I'm going to add it to my neighbor. If you want me to add a base, if I already have one, I'm going to add it to my neighbor. Else, if I don't have one, I'm going to take your base and I'm going to put it as my next, because I don't have a neighbor. Because that means I'm null. So next is true when next is not null. Else means next is null, so give it n. So this is a connecting base to a base. So we're going to add handlers. This is how we're going to add handlers. Now, the next thing we have, so the most important thing that we have here, so this is a construction of a base, setting our neighbor to null. Set next can set our neighbor to whatever we want to. We can add one, and if we have one, we basically add it to our neighbor. Otherwise, we add it to ourselves as our neighbor. The other method is, now this is going to be a virtual method. This virtual method is called handle. And somebody's going to ask you to handle some kind of a job, and the job is going to be an integer. So the integer comes into handle. Handle is virtual. So what I'm going to do is I'm going to say next, pointer, handle I. So if you ask me to handle something with a 5, I'm going to ask my neighbor to handle the 5. I'm going to pass this request forward. Does that make sense? So handle is basically, so the chain method in the base class always delegates to the next object. Okay, so now what we're going to do is we're going to create actual handlers. So handler number 1 is a subclass of base. So that means it inherits. Set next, it inherits add, and it inherits handle. This is virtual, but it's not pure. So it is an actual method. So this is not an abstract class, but it is a base class. So handler 1 subclass is base, and what is it doing here? That's an override, right? How do you know it's an override? Because it has the same signature. Such a good word, signature. It's a unique identifier. Signature is forget virtual. Virtual is virtual. You don't have to repeat that. But it's handle int void. And look at this one. Handle int void. So that's an override. So handler number 1 gets a job to do with an int value of I. If a random number divided by 3, the remainder is
0 by 2.
is true, which means not non-zero, well, what's the probability of that happening? 0, 1, 2. What's the probability of true? 2 out of 3. 66%, right? So 66% of the time, it's going to say cout H1, handler 1, passed the job, I, and then it's going to say base, : handle I. Do you understand what that means? What I'm doing here is when you ask me to handle something, if this condition is true, I'm going to call the method handle, but not recursively. I'm going to call them out of my base class. And what does that base class do? Well, you know what it does. If you call this one, it's basically going to go to my next, and I'm going to say handle to my neighbor. I'm going to pass the job. But if the condition modulo 3 is false, I'm going to say H1 handled this job. So with a 2/3 probability, I'm going to use my inherited passing method, and with 1/3 probability, I'm going to actually handle it. Because I'll return, right? Handler number 2. Handler number 2 looks very, very similar. In fact, it looks identical. Handler number 2 is a public base. It also has an override of the handle method for the job I if rand modulo 3 is true. 1 or 2. Say H2 passed and then call the handle of the job from the base class. Pass it to the next one. Else handle it. So we have a second, so class handler 2 is basically just like handler 1. In fact, it's identical class. Handler number 3, same or different? They're basically all the same. The only difference is that when they handle it, or when they pass it, they say H2 or H1 or H3. That's the only difference. But other than that, they're exactly the same. So again, so we have our base class, which has the pointers. It has the set next. You can add things so they connect to each other. If you don't have a neighbor, then you're going to add it to, if you have a neighbor, you're going to add it to your neighbor. Otherwise, I'm going to make it my own neighbor. And then you have the concrete handlers 1, 2, 3. So here is the main program here. So the first thing I'm going to do is I'm going to seed the random number generator because I need to use that rand method in the program. So I'm going to construct a handler 1, handler 2, handler 3. So remember, when handler 1 is constructed, it's next. So I'm going to draw a picture of this. When handler 1 is constructed, it looks like this. This is handler 1, right? And it has nothing here. The next is null. Why? That's the constructor, right? Yes? Okay. H2 is the handler 2. It also is null. And finally, handler 3 is H3. It's also equal to null. Again, the reason it's null is because they're all being constructed by default constructors which say next null. So now what I want to do is I want to create a chain out of it. I want to link them together. So what I'm going to do is I'm going to say handler1.add, and I'm passing in the address of handler 2. This is a handler 2 pointer, right? Remember, handler 2 is a handler, and next is a handler pointer. So all of these addresses of handler 1, handler 2, handler 3, all the addresses are handler pointers. Is a, because these 3 classes are just subclasses. So what I'm going to do is I'm going to add a handler pointer. What's the value of my next in handler 1? Null. So therefore, because it's null, I'm going to basically, my pointer is null, I'm going to set it equal to here. And then I'm going to go handler1.add handler 3. This time when I say .add, it's going to say, this is not null. So what I'm going to do is I'm going to say, okay, you add. Mine is null, so it adds this one. So they kind of self-link together. And then, what's the last thing going to do? Handler 3 set next, ampersand handler 1. I'm going to, now, is handler 3 set next? Does that have, what's its next value? Null. So if it's null, then this pointer will be set as my next. So what's going to happen is this guy is going to link like this. Get it? So I just created a circular chain. Okay. So now what I'm going to do is I'm going to say so you understand I have this right here? Okay. So once I don't know why this is, I think this should be a small h. Because that's the object. I mean, I ran it, so I don't know why it's showing, I think sometimes if you put it in Word, it corrects it. You know what I'm talking about? Has to be a capital letter. The same. All right, so what happens is I'm going to loop from 1 to 9. And each time, so 1 is a job, 2 is a job, 3 is a job, 4 is a, all the way to 9. So what I'm going to do is I'm going to say 1, handle 1, right? So handler 1, handle 1. So I'm basically telling this guy to handle 1. Now remember how this job works. Basically it's going to generate a random number. And if that random number is 1 or 2 out of 3, then it's going to handle it, otherwise it's going to pass it. So look what's happening here. So when I pass it 1, it says H1 passed 1. So it triggered this one. H2 also got a 1 or a 2. H3 also got a 1 and a 2. H1 also got a 1 and a 2. Finally, H2 handled it. So, handled it. Get it? Now, that's on the first loop iteration. On the second loop iteration, H1 handled 2. Why? Because obviously the value on the random number generator made the condition true. It handled it. It's done. So now we can go to 3. 3 immediately. H1 handle. Oh, H1 always gets the first crack at it. Why? Because it's always H1 handle. So then H1 passes, H3 handles it. Passes, handles, passes, handle, like that, like that, like that. Get it? So this is an example of chain of responsibility. Basically, we made a chain, and now you might say, well, that's kind of a dumb thing. But it's not a dumb thing, because basically, when you pass, it means you're too busy. So you pass it because somebody else may be less busy. If that person is also too busy, they pass it. They keep passing it until somebody has time. And time is probabilistic. So there's a probability that you're going to be having time to do it. In our case, what's the probability? What's the probability for each time I give a job that it will be handled locally? 66%, right? 2/3. So there's a 0.6666 probability that a job will be handled immediately. So that means there's a 33% chance that it won't. So 1 out of 3 jobs will not be handled. And you can see how many jobs were handled. 1, 2, 3. Out of 9. It's 1/3, 2/3. But then it continues the same way. Everybody has got the same probability. Now you might have servers that are faster. If servers are faster, you might have like one server. Now this could be passing between handlers. These handlers could be different servers. So a server could actually be making a connection to a different machine, like to the same machine. That's a fancier way of doing it. That way you might have to, for example, the slowest machine to a faster, so you have a more likelihood that it's going to get handled at the end without cycling back. Okay, in this case, all of the handlers are peers. They have the same power. And so the last example I'm going to give you, I think it's the last example, I'm going to do chain of responsibility, but we're going to have the first chain will be least powerful, more powerful, and most powerful. So basically, if a job comes in, it's too high level for me, I pass it. If I can handle it, I handle it. If I can't, I pass it. The last server or the last handler was going to have all the authority. You can handle anything. So in this case, we're going to have priorities 0, 1, or 2. We can handle those priorities, 0, 1, or 2. Pass higher ones to the next link in the chain. So now, class handler 1 is going to be a little bit different from 2. Before they were all kind of the same. So therefore it says if the priority is greater than 2, 0 or 1 or 2, if it's greater than 2, like 3 or higher, then I'm going to pass it, right? Base, handle, priority. That's a passing one, right? We're going to pass that level job. But if the job is not greater than 2, so 0, 1, or 2, then I'm going to handle it. So if the jobs, so if the range of jobs are 0 to 10, that means I can handle 30% of the jobs. So class handler 2, now it says if priority is greater than 10. So the only time I'm going to get this, I'm going to pass this if it's 3, 4, 5, or 6. So I can handle those values. If the priority is more than 6, 7 or higher, then I'm going to pass it to my neighbor. Otherwise, I'll handle it. And I think the last one I have here is if the priority is greater than 10. Oh, I guess I have 4 of them. If the priority is greater than 10, then pass it, otherwise handle it. So this is going to go 7 to 10. If it's higher than that, I'm going to have class handler 4, always handle, never pass. So this is going to be not like this. This is going to once you get here, it always handles it. Got it? Okay, so that's called chain of responsibility, but now we have, each handler has more responsibility available to him. So we're going to show this like this. So again, handler, 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 right? Capital H. Thank you, Word. Okay, so we have 4 handlers. Handler 1 at handler 2. Handler 1 at handler 3. Handler 1 at handler 4. So handler 1 connects to 2, passes 3 to 2, makes that 1, and passes, handler 1 passes 4 to 2, and 2 passes 2 to 3, they connect to each other. So now I have a jing, 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 4 of them in a row like that. So now I'm going to go for int I equal 11, decreasing by 3. So it's going to be 11, what's next? 8, 5, 2. Okay. So what I'm going to do is I'm going to say here, handler handle. So the first value is 11. So H1 passes 11, H2 passes 11, H3 passes 11, and finally H4 handles 11. The next value is 8, H1 passes 8, 2 passes 8, H3 handles 8. Okay, when we get to 5, H1 passes 5, but H2 handles 5, and finally when the level is only 2, H1 handles 2. So this is chain of responsibility, but this time we are having increasing levels of responsibility. So from the lowest to the highest. Once the last one can do anything. This pattern, I know I said it was going to be the last one, but I kind of mentioned it before, so I'm just going to very briefly talk about it. This is the observer pattern. This is when somebody's looking at something. So we have there are 2 classes that are involved. One is the observable class, that's the subject. And one is the observer class. That's typically an abstract class providing the interface with concrete classes interested in events that they can synchronize or coordinate with. Okay, so observable is what we were looking at, and observer is the abstract one that's looking at it, but implemented by concrete observers. So abstract observer, and then we have concrete observers observing the observable object. So this is the observer abstraction. This is the concrete observer. This is another concrete observer. So they all have that. Like, let's say the method is called notify. And this is the subject. We're looking at the subject. We're looking at this guy right here. See, what's he going to do? Well, he's going to move that camera. So as soon as he moves the camera, I go like this. You know. Okay. Okay. So we're watching this through this interface with these observers. Okay. So I promise it's going to be the last one. Stop it. Don't get so much kick out. Okay, so this is going to be the virtual class called myObserver. So we'll have a method called notify, which is pure virtual. So that's going to be right here. Okay, pure virtual. So that's our abstract class. Sometimes we call that an interface. But keep in mind, abstract classes can have properties that are real and methods that are real. But if they have one method, which is pure virtual, they are abstract. Okay, so now what we're going to have is we're going to have a real class. So we're going to say, or actually my observable, this is going to be what I'm looking at. So I am looking at this thing, my observable, this is the subject that I'm looking at. And so I have an instance, and an instance is basically a pointer to my observable, which is one of these things. Okay? And then I have a set, which is a STL, right? A set of my observer pointers called observers. So I can add, I can remove, right, like that. And then I have a constructor, my observable. So the public interface includes getInstance, and you've seen that before, right? So getInstance is going to give us a pointer to one of these things. We can add an observer and we can remove an observer, because basically, let's say something happens, like he moves the camera, so I want to go like this, and you guys want to go, ha ha ha. So that's two observers. I'm observing and you're observing. When he turns the camera, you laugh, and I go like this, and so that's two observers. So you can add observers, okay? And then we have a method called notify observers. So basically, when some event happens, you want to notify the observers. So this is a typical type of design pattern for event handling or events happening. Oftentimes, GUI events are handled by handlers or delegate handlers that do something when something happens. Click a button, you might want to print something. Okay? You click on the X, you might want to close the window. So those are well-known observers, but you might want to have your own observers. For example, when somebody goes over my GUI, I want to change the color of the GUI to show that I know that you're on here, and then change it back when you're off. So that's an observer too. You can add it, you can remove it, you can have multiple observers. So that allows the observable object to basically have many observers by adding them or lessening them by removing them. And then also, I want to be able to notify my observers. How do I know where my observers are? Because I have a set of them. So how do I get them? Well, I can basically use an iterator, right? And then I can do my begin, end, and I can go through all of these observers that way. Okay. So this is going to be the CPP of the my observable class. Here is basically, I started as null. If I want to get an instance, if instance is equal to null, then I create my observable. So I create it when I need it, right? If I want to add an observer, they're going to give me my observer by reference. I'm going to insert this into my set. That's using STL, insert. And okay. And if I want to remove it, I'm going to erase. And I'm going to send the pointer, right? The pointer to this thing into observer. So I can insert into the set, which adds an element. I can erase from the set, which removes that. And then finally, I have notify observers. So when some event finally happens, what I'm going to do is I'm going to get an iterator for the set from here, right? And then I'm going to say for it equals observers begin. You know this very well. Okay? It not equal to observers end, it plus plus, star it, pointer, notify. So this will basically go through a set of observers that are still there, because you can add them, remove them. I'm going to look at the ones that are there, and I'm going to iterate over them and call notify for all of them. And then I have a method which I call trigger, and trigger will basically notify the observer. So this is just for testing. I can see that if I call this method, I should be able to notify all the observers that something is going on. Okay, so now I think this is a problem here. So I think the class should be called something different. It should be my observable, I think. So this is a new class. It's a subclass of my observer. Okay, and so I have a pointer to my observable, and so my observer, maybe this should just be observer. I think I kind of got confused here. So my observer constructor basically gets an instance and gets the observable, and then it basically says observable pointer add observer this, which adds itself. And the notify is going to be received a change of event. That's just the way we're going to see it. So now we're going to see how it's going to work. So we're going to create my observable get instance. So we're going to get a my observable pointer here. We're going to go to my class pointer obj equals new my class. And then we're going to go to observable, and we're going to, for testing purposes, we're going to trigger this. And so now we're going to have received change event. Example. Okay. I know I said I was going to be the last one, and this is the last one, but I'm just trying to show you that the iterator design pattern is a design pattern that's implemented already in C++. So if you look at these notes, it's just basically what the iterator does. Java does this using something called enumeration or iterator as well. So I'm not going to go through that. Iterator, and that's really the last one. So iterator is a pattern that allows you to go through the elements of a collection of objects without knowing how that collection is organized, without having access to any properties, pointers, or addresses of anything, or arrays or vectors. So you basically iterate without knowing the structure, and that's the iterator design pattern. Okay, and that is the last one. All right, so anybody have any questions? So these guys are finishing the project. When is the project going to be due?
They finished their several system last assignment.
It's finished?
Yes.
Submitted?
They submitted, yes, and
Anybody need any extra time, or everybody's finished?
everybody finished.
Needs extra time?
Oh.
Okay, you still working on it? Okay, so talk to him after class. You're going to see what he can do. Okay, that'd be nice. He's a very nice fellow.
Yes.
Basic design, pattern, code, understanding pointer code, understanding all the stuff we've been talking about in class. Please make sure you are very comfortable with char pointers. Because I always give you some examples of char pointers, some functions. So you have to, or in pointers and things like that. You should know, I'm not going to ask you to write any code, but you should understand what is a functional pointer. You should understand what is a double pointer, in pointer. You should understand pointer arithmetic. You should understand star value, multiple levels of dereferencing. You should know the difference between a pointer and a reference. That can be tricky, but it's not that hard. What type is ampersand k when k is an int? In pointer. That's just an in pointer. It's an address of an int. Okay, if we want polymorphism to work, then we need to pass our parameters by reference or by pointer. If we do not pass them by reference or by pointer, then we will not have what kind of binding? We will have early binding, and the binding will be connected to the type that's passing by value. That's what we talked about. Okay, so that's very, very important. So, like that. Can we pass pointers by value or by reference? Which way can we pass pointers? By value or by reference? Both. It's up to us, right? So a pointer. When would we want to pass a pointer by reference? When we want to change the actual pointer. Actual pointer. Remember, we have actual, formal. So if you want to change the actual, if you want to change something actual, you got to pass it by reference. Can we pass a pointer to pointer by reference? Yes, why not? It's just type. How would that look like? Int star star reference pp. So pp is an int star star passed by reference. So imagine what that would look like in a function header. That'd be very confusing, right? If you pass a pointer to pointer by reference. What's the star value of an int pointer reference? not a trick question. What's the star value of an in-pointer reference?
1.
Who cares if it's a reference or not? It's an in-pointer, so the star value is 1. What's the star value of an in-pointer by value? 1. All right. Go through the different sections that we went through. Be familiar with basic STL, how we go through things like, so STL, you should be familiar with vector, set. What else do we cover in vector in STL?
Maps.
Maps, yeah, okay, thank you, yes, maps. So those are the key ones, because maps you have the key and the value. Remember how to template a method, like we looked today. Like the binary search we did, and then what's the other one we did? We did another templated method today. Which one was it? For example, I don't think I'm going to ask you to write a method, but I could ask you, but I could give you a template method and then ask you questions like, will this work with our rational class, yes or no? And then you have to tell me why it would or why it wouldn't. Again, why would a template that works with one class not work with another class? That's a question I could ask you, and you have to give me a few words. Why would a template work with one class but not with another class? What would be the answer for that? Because some of the operators we're using might not be defined for another class. Okay. Macros. Make sure you know how to read macros. Remember our macros with parameters? If you define a macro with parameters, and the macro is called ABC, ABC, what's the next thing that must follow? Macros with parameters, ABC, what's next? What is that? Parentheses. Any space allowed? No. So macro parameters must be followed immediately by the open parentheses. Must be. Otherwise, it's not a parameter. How many parameters can you have in a macro? 1 or 2? Or 3? Can you have 1?
Yes.
Can you have 2?
Yes.
Can you have 3? Yes, 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 yes. Max, parenthesis, A, comma, B, comma, C, comma, D, close. And then code. What's another? What is a good simple name for a preprocessor? What is that? What does a preprocessor do? String. String substitution, acceptable. String replacement, like that. Okay, that's really what it is. Remember the questions I asked you about stack frames. All those things just kind of keep in mind. We talked about recursion, how recursion is implemented using stack frames. Okay, so lots of things to look at. Look at the quiz, look at the midterm exam, kind of review that. Look at all the material. Obviously, I'll probably tend to go, you'll be covering the whole material of C++, but I'll probably tend to go more towards the end stuff. So if you're going to, because the other stuff you know what an int is. You know what a double is. You know what an int pointer is. That's too easy. You know what P++ means, right? So review from midterm on especially. Okay, and I'll try to make it not terribly difficult, but I want to make sure that you are studying well and preparing and knowing the information. Okay, it's a good language. I think you guys are a very good group, right? You guys are a nice group. I enjoy teaching this class. You guys are very attentive, very serious. Serious class, and I think you guys think you learned a lot this semester for this class. No? Is it a yes or a no?
Yes.
Was it too hard or was it just hard enough?
Hard enough.
Hard enough, right? Not too easy though, right? Not too easy. Okay. All right. So I tried not to give you overwhelming amount of programming, but you needed to do some programming just to make sure that you were honest and learning the concept and trying things out. How many of you tried some of the code from the lectures in your C++ compilers just to make sure they worked? And I wasn't just making stuff up. Okay, if you did that, I bet you're going to get the best grades. Because that really teaches you. You try it. Okay? So you still have time to try a few things. If you're not sure if something works, try it out. Okay. Have a great day.